qualitatively discussed the competition between nucleation and growth, i.e., so nucleation, the driving force here is thermodynamic, growth, driving force there is kinetic in nature. But now we're going to get a little bit more quantitative in terms of our discussion of this competition of growth, nucleation, and where we can maximize our crystallization rate. So let's think about kind of the factors that go into spherulite growth. So basically the rate at which we add essentially polymers to our, so this is one polymer, how do we add this next kind of lamellar to here and this lamellar to here? Well, it has to diffuse. So it's going to take time for our polymers to diffuse and move towards this growing face so we could kind of elongate our spherulite branch. So remember, our spherulite circular in nature, and those lamellar grow out like this. So we need to diffuse, key term here, into this growing edge and then move across. So diffusion is basically, we've talked about this. If you haven't taken my NGR 45 course, you could look at my UOP, my OER textbook for ENGR 045, and look at chapter 4, kinetics. It's a deep discussion on diffusion, but we know that diffusion is just this temperature activated process, kind of this stochastic random jumps, and we know that we can write diffusion. Let's go here. This is the graph that we saw last time. Again, this critical R, you can kind of think of it as our lamellar. This is kind of just this general relationship, but we could plug in for specific R delta G is minus delta GV times, again, that volume plus that delta GS term. So way back previously in our derivation for spherulites, but we're getting a little off topic. So we know that diffusion, D approximately equal to this. Usually you'll see this prefactor exponential minus QA over KT. So this is an activation energy, so just some barrier for diffusion that we have to jump over. And then this KT, this kind of relationship, this exponential minus an energy over KT is referred to as an Arrhenius relationship. Arrhenius relationships pop up all the time in material science and biology and everywhere. So the key thing here that you'll see in this expression is the lower the temperature, i.e. so as my temperature decreases, as my undercooling increases, we see that my diffusion will slow. And again, that kind of makes sense because at low temperatures, again, it's this thermally activated process, so our number of jumps decrease, and so our diffusion slows. So lowering the temperature below the melting temperature will slow the transport of polymer growing to the spherulites. So when you look at kind of how diffusion will occur as a function of delta T, so at large values of delta T, this is going to kind of be, again, it's going to die off. So very low values here, very high values here, so it could kind of die off like that. So it shoots up at these low values exponentially right here. So you could just kind of plot that out. And the same thing, if you could plot it as a function of T. Now in exams, I really like to kind of give these types of problems where either I'll give it as a function of T or delta T to kind of test that relationship. So be aware that that might be a possibility moving forward. So growth, I think, is a very intuitive process. Like diffusion, I think people understand that well. Lower temperatures, lower diffusion, and then we'll get into nucleation, and we actually already have done quite a bit in the next video. We'll go over it one more time and kind of see what goes into that calculation. So we'll see you all in the next video for nucleation. We've done growth, your master's of kinetics, now it's thermo time.